Alright. Selamat pagi, selamat malam, selamat siang, selamat sore. Those are just how to say good morning, evening, afternoon in Indonesian. Welcome to, unlike the plenary on Monday, this is a language I actually speak. Welcome to what is now our 8th plenary talk for the Student Symposium in Combinatorics 2022, a conference for students by students in combinatorics and related disciplines. If you're joining us for the first time, well, just for the plenaries, welcome. This symposium is supported by Matrix, the Australian Mathematical Society, the Australian Mathematical Sciences Institute, and UNSW Sydney. We're very grateful for their support. So it is my great pleasure to do the introduction to the plenary talk of Fransisca Susan. I think one of the things that we're most proud of as the SSC committee is our list of plenary speakers. That's one of the things we spent the most time on. And because of the nature of our conference being very much about early career researchers and about building collaborations and connections with people, we felt that the person's story is just as important as their research. And I think Susan is the perfect person for me to highlight this, not so much because I happen to know her personally, but because I happen to know her story quite well. Susan is a fourth-year PhD candidate at MIT's Operations Research Center, advised by Nengin Reze. Her research includes online learning, machine learning, combinatorial algorithms, approximation algorithms, and mechanism design. She also did her undergraduate at MIT with majors in maths, electrical engineering, computer science, and a minor in economics, an incidental minor here in economics. I must admit that we were a little bit concerned when we sent out the invitation to Susan to give a plenary, because we did so around about the same time that she was getting quite a bit of publicity for something in particular. And we were worried that she couldn't possibly have the time to talk at our humble conference that no one had ever heard of. Concurrently with doing her PhD, she is the Chief Technology Officer of the Indonesian startup Seribu, which she co-founded in 2020. And Seribu is an app launched last year with over 100,000 users that helps young people manage their personal finances and aims to promote financial literacy in Indonesia. And together with her Seribu co-founders, she was part of the 2022 Forbes Asia 30 under 30 list in finance and venture capital category. And that's why we were a little bit worried. So I actually have a little slide I want to share. So Susan and I met Susan a very long time ago when we were in primary school, and we met through Maths Olympiad training camps. I went through the archives to try and find pictures from those times, and I only found one set of pictures. I won't point out who we are, which one's us, but this is us receiving awards at award ceremony in Indonesia for the Australian mathematics competition. So actually, there's an Australian connection there. I guess after a couple of years in the Olympiad world, I went, I can't take this anymore, but Susan persisted, and I guess it shows in how differently we ended up today. But yesterday we had an estimathon as part of the SSC social events, and part of the estimathon, people learned that Susan is the first Indonesian woman to have won medals at the International Mathematics Olympiad. In fact, she's got 3 of them. And for achievements in this space, she was awarded what we call a Satya Laksana Wirya Karya, which is a presidential medal of honor awarded to Indonesian citizens. And for Australian audiences, I would describe this as sort of the Indonesian equivalent of the Medal of the Order of Australia. And she got this while she was still in high school. So I think that it's sort of very safe to say that Susan is one of the most prominent figures in Indonesian mathematics, not so much because of the medals and the achievements, but more so because of how she's used the platform that sort of comes with that. So Susan's sort of given quite a lot of interviews on the internet, too many for me to catch up, to keep up with, right? And I think one of the things that I find particularly inspiring about Susan is that she's really, her talking about her relationship with maths has really broken a lot of stigmas that we have in Indonesia about doing maths. I, for one, feel a little bit less of a failure for doing maths because that's what I've seen Susan do it and achieve. I just wanted to end with one little anecdote, which is about one of our fellow PhD students here at UNSW has has a podcast series in Indonesian where he interviews Indonesians who are in mathematics all around the world. And yeah, so he couldn't have had this series without Susan. And Kevin told me about it, and I mentioned it to one of our undergrads who happens to be Indonesian as well, and it's now one of our most valuable undergrads in the school. And when I mentioned this to her, she went, "Susan is the reason why I'm doing maths." And I think that's sort of, no matter whether or not you realize it, Susan, that's actually quite a thing that you hear a lot. And so I feel the weight on my shoulders of doing this intro justice, because I know that there'll be lots of people watching this on the internet afterwards. No pressure there. So I hope you will all join me in welcoming Susan through virtual applause as she talks about online learning via greedy algorithms, via offline greedy algorithms, applications in market design and optimization.
Okay, thank you. That was quite an introduction. Yeah, with the picture and stuff. I can start sharing my screen. Yeah, so hi everyone, I'm Susan. I am a fourth-year PhD student, as mentioned before, in operations research at MIT. And I think, I guess in terms of combinatorics, I don't know how much combinatorics I'm using in this work. Probably way less than the talk that I've gone to before in this conference, but regardless, I hope you can enjoy it. I'm also based in Boston, so I'm in Cambridge, but yeah, but if you're around here, I would always love to catch up over coffee or food. So yeah, let me know. So today I'll talk about my work in online learning via offline greedy algorithms. And there are essentially two sides of this talk. So in one side, we have the offline problems, mainly combinatorial offline problems and their approximation algorithms. And on the other side, we have real-time decision-making environment. So an online learning environment where we are trying to use the offline algorithm to make efficient decisions in a time varying setting. So I'm going to talk about some generic tools to do such transformation. And usually to make things easier, I will talk in terms of examples, and I will touch several examples in revenue management and market design. And this talk will be relatively high level, but it's based on the paper with the same title. So I hope by the end of this talk, you would be interested enough to check it out on arXiv. Yeah. Oh, so also this is a joint work, sorry, with Red, Megan, Ashwin, and Josh. Okay, so the main theme of this work is really trying to use the best out of the real-time aspect of the problem. So the fact that there are users in online platform that continuously feeding data to the platform, and the platform wants to learn as fast as they can while not making too many suboptimal decisions. Okay, so these are motivated by, so in my field, a lot of work has to be motivated by applications. So these are motivated by some real-time operational decisions. And especially with the rise of online marketplaces, we can see them in terms of shared economies platform, internet advertising, or even cloud platforms when they're trying to optimize their computing loads. So with the rise of online marketplaces, they definitely become more prevalent. Oh, also apologies in advance if like I cough or like, yeah, I cough in the middle or I start losing my voice. I am recovering from COVID, which unfortunately takes me quite a while, but getting there. Anyway, so the things that all these interactions have in common is that there is a real-time interaction with users, and the fact that through these real-time interactions, the platform try to learn their users' behaviors and optimize for each decision in order to achieve some economical goals. But in doing so, they face several obstacles. I will categorize them into like three major challenges. So the first one is future uncertainty, which is really coming from the real-time aspect of these applications. The second one is the time-varying environment, which comes from the dynamic aspect of these applications. The fact that users' behavior are changing over time. And finally, there's also the computational complexity, which comes from the fact that the decision maker needs to make a decision from a large set, or like if there's some combinatorial aspect in terms of the decisions that they can choose. So given these three challenges, the high level goal that we want to do in this talk is how to do decision making through learning and optimization as if these limitations had not existed. And basically, we want to do so by minimally changing the offline algorithms so that they work with all of these challenges. So I will elaborate this more later, but before that, let's look at like some even more tangible examples that suffer from like these challenges. Okay, so there are many more examples, but these are just the ones that I remember the most. But anyway, so for example, the first one is assortment planning. Like in assortment planning, like a store manager wants to choose a set of items, usually of certain size, that they can display to maximize market share. So like market share here is like the probability that a user will buy something. Or like in the product ranking example, usually customers have more limited patience and attention. So like the problem here is like how can the platform rank items to maximize the probability that some items are bought? And another example is in the online space too. It's related to the ads auction, where a platform wants to set personalized reserve prices for each bidder in a way that extract the most revenue out of them. So yeah, maximizing revenue, maximizing market share is a common theme usually with all of these problems. So those are that is the economical value that they want to maximize. And again, repeating what was on the previous slide. So there is a future uncertainty and time varying aspects, since like the demand or like customers behavior, or even in the last application, it's like the bidder valuations, they are changing over time. And all of these problems are also combinatorial. So even without uncertainty, the offline problems are usually NP hard to solve. So for example, like in this assortment planning problem, if there are n items and they want to choose like a set of like k items, there's at least like n choose k like possible sets to consider. But like all of these problems admit greedy heuristics that approximate the optimal solution up to some factor. And these are like the works of the greedy heuristics. So I will use this example as a running example in this talk, which is the assortment planning example that wants to maximize market share. But in general, the research questions that we're trying to achieve here is that how can we design learning algorithms for such combinatorial problems? Like, can we efficiently transform the existing approximation offline algorithms to their online counterparts such that we have sublinear regret? So the answer is yes, we can for a large class of problems that admit a robust greedy algorithm with a constant approximation factor. And to explain more about what a robust greedy algorithm is, and also like illustrating the technique, I will go deeper into like the assortment planning example. Okay. Okay, so actually I need to drink some water. So in the assortment planning example, we have n products, and the goal is like to choose a set S with at most k items that maximizes market share. Here we have f of s, which is a function. It's a monotone submodular function that represents the probability that at least one item in the set S is being purchased. And we want to find a set that maximizes this function f of s with cardinality at most k. And this offline problem actually has like a greedy algorithm with 1 minus 1 over e approximation factor. And this is a tight approximation factor. This is by Nemhauser et al. So this is the greedy algorithm for the offline problem. It's a quite simple greedy algorithm. So like it starts from an empty set, and then like each subproblem here decides which item to add to the set. And because it wants to add k items, so there are k subproblems here. And then for each of the subproblem, it greedily picks the item that maximizes the marginal market share given the previous set being chosen. And then after it finds the item that maximizes the marginal market share, it adds it to the set and then goes to the next subproblem until it has k items. So we can think of the algorithm as like building the solution stage by stage, or like subproblem by subproblem, where at like each stage, it picks the product that maximizes the marginal market share function. Okay, so if we now consider the online version of the problem, where there are big T periods, in round T, small t, like the nature or like the adversary can like choose a monotone submodular market share function f of t, and the algorithm doesn't know this, and then it wants to choose a set s of t to offer without knowing the function f of t. And then afterwards, it will receive like the market share function or the reward f of t of s of t. And at the end of each round, the algorithm gets some feedback. So in the full information setting, the algorithm observes the full function as the feedback. But in the bandit setting, it only observes the function evaluated at the set that was submitted by the algorithm. So after laying out like the problem setting, I'll talk about like this is the main results and the contributions of the work. So we designed an efficient framework to transform offline greedy based algorithms to their low regret online counterparts via Blackwell approachability for both in full information and bandit settings. And generally we get square root of t gamma regret for a full information setting and t to the 2/3 gamma regret for the bandit setting. We also prove some lower bounds on the regret. And in our running examples from before, which are these ones, it's equivalent to the problem of maximizing a monotone set submodular functions with cardinality constraints. And we matched the previous gamma regret bound by Streeter and Golovin for the full information setting and improved the bound in terms of t for the bandit setting. And it has a wide range of applications from product ranking, gain reserve price, and a bunch of submodular maximization with several settings. And here are the updated bounds compared to the previous bounds. So again, in general, square root of t dependency for the full information setting and t to the 2/3 dependency for the bandit setting. That's for the discrete problem. And for the continuous problem, we have t to the 4/5 dependency for the bandit setting. And usually the extra t term here is because of the discretization error. And even though like the bandit structure captures like more realistic scenarios, but there have not been a lot of work that consider this like bandit setting. And I'll go quickly over some related works. So in the area of like offline to online transformation, Hazan and Koren presented a negative result saying that there is no general offline to online framework that exists for like general combinatorial problems. Then Kawai and Vempala with Follow the Perturbed Leaders and Dudik et al. With recently in 2017, they presented a framework for offline problems that can be solved efficiently. And then in terms of combinatorial learning literature, previous works mainly focus on linear rewards. So on the other hand, we focus on like NP-hard problems with nonlinear rewards. Compared to the previous works, we don't need the offline problems to be efficiently solvable. But because of that, we have gamma regret instead of like one regret, and we narrow the space of the general combinatorial problems by only looking at those that admit like the offline greedy heuristics. Okay, so now we want to characterize the offline problems that we work with. So in this sense, we both identify like simple generic conditions under which such a transformation exists, but also we want to show that our characterization comprises of a large and diverse class of problems, and a lot of applications can fall under it. Okay, so revisiting the greedy algorithm we have for the assortment planning problem, there are K subproblems again, and for each subproblem, we're picking like the product Z of I here that maximizes the marginal market share, which is like delta F here. So in this notation, delta F is a function of the current set and the item. And then if we define a factor valued function called payoff, which is a function of the item, the current set, and delta F, then we can see that choosing a product Z of I such that it maximizes delta F function is the same as choosing Z of I such that this payoff is non-negative for each of the coordinate. Because if we see here, the jth coordinate of this payoff function is actually the difference between the marginal market share at Z of I and the marginal market share at the item J. Now, the problem is that this payoff function is not linear in terms of the greedy decision Z of I. And it's much easier to work with like bilinear payoff. So we want to linearize the payoff function. So instead of considering the item, we consider the distribution over all products for each subproblem. So instead of picking one product, the subproblem picks a distribution over all items that maximizes the expected marginal share, the expected marginal market share. So here, subproblem I picks theta I instead of Z of I, then the delta F function becomes the expected marginal market share, where the expectation is over the distribution theta I. And always picking Z of I is actually equivalent with putting the mass equals to 1 for Z of I and 0 for all of the others, for all of the other items. Now the payoff function is linear in terms of theta I, which is the greedy decision. Okay, so the first character of our class of problems is this one, which is that it admits iterative greedy algorithm that is robust to local errors. So what does that mean? It means that if we replace the locally optimal decisions with almost locally optimal ones, the sum of the errors, they don't blow up at the end. So as we can see, For the errorless system, if we have non-negative payoff at each time, then the final set chosen is at least gamma times the optimal. Now, for the system with the local errors, if theta I is replaced with theta I tilde such that it's epsilon far away from the optimal, then the final set chosen would be at least, at most, epsilon times k away from gamma times optimal. And here k is like the number of subproblems. So essentially the local errors here do not propagate badly. And not all greedy algorithms are robust. And we actually need a stronger version of robustness, which we call extended robustness, where like the errors still do not propagate, even if we sum them over all rounds. So if we consider a noisy run of the algorithms over like big T rounds, and for each subproblem, the sum of the payoff is at most error T away from the optimal, then the final sum of the rewards or the values over the T rounds would be at most K times error T away from gamma times the optimal. So this is extended robustness. And the second character of the problems that we need is Blackwell locality. So like each iteration of the greedy algorithm should be able to be casted as a Blackwell game. And I will talk more about this later when I'm talking about Blackwell sequential games. But for now, those are the two characters of the offline problems that we are considering. Okay, so now going to the approach. The high level idea of our framework is that, so now if we have the offline problem, we know the function f at each time. So we know the optimal theta I. But in the online problem, we don't know f of t. So we need a subroutine for each subproblem that can return a distribution theta I tilde such that the overall error made by all the subproblems over all rounds is not big. Let's say it's at most error of t away from the optimal. Okay, so if we want this error t function to grows like square root of t, and if we succeed in doing so by the extended robustness property, we would get k times square root of t gamma regret. But then the question is, how do we design an algorithm for each subproblem such that error t grows like square root of t? So this is where we're using Blackwell approachability. So to do that, I'll go briefly over Blackwell sequential games. So it's a repeated two-player zero-sum game with vector-valued rewards. On each round t, player 1 plays x of t, player 2 plays y of t. Then player 1 obtains some reward, r of x of t, y of t. This is a vector. And player 2 obtains the negative value of that. And these rewards R is by affine in terms of x of t and y of t. In a Blackwell game, the goal is P1 wants to approach a convex set S, and P2 wants to avoid this from happening, essentially. And there's also a notion of G of t approachability in this Blackwell game. So a convex and closed target set S is G of t approachable if there exists a strategy for P1 such that whatever P2 plays, the distance between this set S and the average payoff is like the average vector valued reward is at most G of t. And ideally, we want this G of t function to goes to 0 as t goes to infinity. And there's another notion of approachability, which is called one-round approachability, where a set S is approachable if for every action, for every P2 action Y, there exists a P1 action X, such that the reward is in that convex set S. And the approachability theorem says that for any approachable set S, there is an algorithm B such that S is G of t approachable, where G of t grows like t to the minus 1/2. So we will utilize this B a lot for the full information setting in designing our subroutine. So like revisiting the high level idea again, if we replace the greedy step with a subroutine, we will use argb in terms of replacing this greedy step with the subroutine. So essentially, argb will handle each subproblem. We will have argb instance, one instance for each subproblem, and we can think of each subproblem as a Blackwell game, where P1 is the algorithm and P2 is nature, giving us the function delta f at times t. And after defining our target set and proving that it's approachable, we can use arc of b such that error t grows like square root of t. So specifically, if we think of the greedy algorithm as a Blackwell game, so P1 is the algorithm. It wants to play theta t tilde on each round. And then P2 is like the adversary, choosing the delta f function at time t. Then the payoff vector here is by affine factor in terms of the tilde and delta f. And we want this payoff to be non-negative, so we can choose the target set to be the positive ordered. It's convex and closed. Well, positive ordered bounded at some values. And it's also approachable. We can prove that it's approachable. And because it's approachable, we can approach the set S with arc of B such that this error grows like t to the 1/2 and times log n to the 1/2. And the remaining questions is, how do these Blackwell subroutines for the different subproblems communicate with each other? Because each subroutine has like its own, but they haven't talked to each other. So the way they communicate is based on the original greedy algorithm. So for each round, after the algorithm runs k arc-b's, like the algorithm gets the final set and then it submits it and it gets back the feedback, which is the f of t function. And then it returns back the f of t function to each of the subproblem. It returns it back to each of the arc of b subroutine. So our analysis shows that if arc b accumulates error that is upper bounded by this t to the 1/2 times log n to the 1/2, then the total gamma regret would be k times that. And this is a more general version. Essentially, it says that if an offline greedy algorithm is extended robust and Blackwell reducible, then the total gamma regret would grow like t to the 1/2. And this transformation works in polynomial time. And there's this Blackwell reducibility term here, which is the second condition on our offline problems. So essentially, it makes sure that each problem can be handled by replacing the greedy step with a Blackwell subroutine. So in terms of the proof is pretty simple. It connects back the Blackwell payoff with the payoff from the offline algorithm. Then it used the robustness property, which I will skip for now, but it's on the paper. But then for the bandit setting though, there are more challenges because if before for each subproblem, for each subroutine, it gets the function f of t. Now on each round, what we get is only f of t at the submitted point. Like in this case, it's only at the submitted set. So because each subproblem needs a feedback, but we can only get one feedback per round. So we need to carefully choose which subproblem and also at which point we want to evaluate to get the feedback. And to do so, we can randomly choose the subproblem that we want the feedback from and use importance sampling to essentially estimate the payoff function. And for this, we need a new notion of Blackwell game. So one of our contributions includes defining this Bandit Blackwell sequential games. So in the Bandit Blackwell games, at each round, there is an extra decision, which is whether to explore or not. If we choose to explore at that round, we would get an unbiased estimator of the payoff. Let's say it's p hat, but it has to pay this cost d of p hat. And if we don't explore, there is no feedback, but there's also no punishment. This d of p hat, we are assuming this is a diameter of p hat. So essentially, we're assuming that whenever we're exploring, we just lose the whole rewards. So at round P, just like the Blackwell games, P1 plays X of T, P2 plays Y of T, and then P1 obtains this payoff function, P2 obtains the negative of it. If P1 chooses to explore, then it observes an estimated version of this payoff function, but if not, it doesn't observe anything. There is another equivalent notion of approachability here. So it says that a convex and closed target set S is G of T bandit approachable if there exists a strategy for P1 such that no matter what P2 does, the sum of the average payoff, the sum of the distance between the average payoff and the set S and the penalty over the T rounds is at most G of T. And ideally, we want G of T to go to 0 as T increases. There exists an algorithm ACBB such that G of T grows like T to the minus 1/3. This is where we get the T to the 2/3 because again, here we're talking about 1 over T. So if this is multiplied by T, we would get the T to the 2/3 regret. And essentially, we're using that ACBB to replace the greedy subroutine at each subproblem. So again, like subproblem 1, the ACBB decide explore or not. If not, it locally updates it depending on the ACBB decision. If it chooses to explore, then it would pick a point where it's exploring at, and then it would get a feedback that is an unbiased estimator of the real feedback. So a problem is Bandit Blackwell reducible if it is both Blackwell reducible and the payoff function can be unbiasedly estimated. And if at all subproblems, the ACBB, like for each of the subproblem, decides not to explore, then at the end it would submit like the locally optimal set depending on the ACBB. So for the previous greedy algorithm and the previous monotone submodular maximization problem, so essentially to estimate this payoff function, like to recall, the payoff function here is the difference between the greedy solution and the marginal value at each point. And then to estimate this payoff function, we can choose randomly an element from 1 to n, and then with probability 1/2, we would include that item to the set, and with probability another 1/2, we're not including it, so we can estimate the difference, and the expected value of this estimation would be the payoff. So then, more generally, we have this theorem for the bandit version, which is if a greedy algorithm is extended robust and it's Bandit Blackwell reducible, then there exists an online algorithm such that the gamma regret in the bandit setting is at most it grows like T to the 2/3. And in terms of the proof, we are fixing the number of exploration round first, and then we're taking the expectations over all the exploited rounds. Now I will briefly touch the applications that I've mentioned before. I think the first one is product ranking. Yeah, so sorry. Okay, so for product ranking, again, the goal is to decide where which item goes at which position, and usually in this setting we have a set a discrete set of customer types, where each customer type considers this, like, let's say the type U considers only the top theta U products, and then they have a function kappa U, which is a function of the set of items, and that's the probability of them buying any of the items. And usually we're assuming this kappa U is submodular. So the goal here is to maximize the expected probability of purchase, where the expectation is taken with respect to all customer types. In terms of greedy, we have n subproblems, one for each position, and these are the updated regret for the full information and bandit setting. And we can do so, we can apply the framework because the greedy algorithm is extended robust and Bandit Blackwell reducible. In terms of the second price auctions, so for this example, the goal is to maximize revenue. So essentially, we're assuming that there are n bidders. One second. So for each of the bidder, we want to choose a reserve price, and the revenue here is the sum of, for each round, it's the maximum between the second highest cleared bid and the reserve price for the winner, which is like the highest bidder. And in terms of greedy, we have n subproblems here, usually one for each bidder. So each stage would maximize the good reserves for each bidder. And again, the corresponding greedy algorithm, this is by Roughgarden and Wang, is a 1/2 extended robust algorithm. It's also Bandit Blackwell reducible, so we get this bounds. And this is the example for the non-monotone continuous submodular maximization. Usually, we find this non-monotone continuous submodular functions in terms of influence maximization, where we want to choose a set of people that maximize the influence. Usually, there is this target function, which is the revenue minus the cost. They're non-monotone and they're submodular. Yeah, the greedy version, the greedy offline approximation algorithm for this problem is the bi-greedy algorithm, which is tight approximation wise, and these are like the improved regret bounds. But in general, I would conclude the talk by saying, by talking about the takeaways. So essentially, we design an efficient framework to transform offline greedy algorithms to their online counterparts that have low regret via Blackwell approachability for both full information and bandit setting. And the greedy algorithm here has to be extended robust and Blackwell reducible or Bandit Blackwell reducible. And in general, we have square root of t regret for the full information setting and t to the 2/3 regret for the bandit setting. And they are tight in terms of there are examples that we can create such that the regret has to be at least that for both the full information and bandit settings. And with this framework, we get improved regret bounds for many applications in revenue management and market design. And yeah, so thank you for listening. That's the link of the paper, and you can always shoot me an email at fsusan@mit.edu.
Okay, thank you so much, Susan. Could I please invite the audience to join me in thanking Susan for that talk? We'll open up for questions now. There's a Q&A feature for you to use to send your questions, and it might take a while for people to type up their question. Oh, well, it didn't take too long, so I might reserve let the audience ask before I ask. So Mark Denker asks that in the bandit setting, does the adversary get to change their submodular function at each time step? And if so, how can past rounds inform strategy for future rounds?
So yes, because we're considering like an adversarial setting, so they can change it at each time. So it's not stochastic in terms of it's not taken from like a distribution or something. So so how can past rounds inform strategy for future rounds? Okay, so I think the thing is that the way we evaluate, the way we define regret is usually with it's compared to the best action overall rounds. So like it's the best, the action has to be the same overall rounds. So the way the past rounds inform the future rounds are by kind of balancing all the actions, such that with respect to like an action that is always the same for all rounds, the regret wouldn't be that much different. I don't know if that answers the questions, but essentially because the adversary can change the submodular functions at each time step, we cannot use the benchmark that is too strong. Essentially, we cannot use the benchmark that is able to change their action at each round, but we're using a benchmark that always plays the same action at all rounds. So in a sense, it's a weaker benchmark, but yeah.
Okay. Yeah, so Mark says that that does seem to answer his question. While we wait for potentially other questions, I wanted to ask, sort of, these sort of transformation results seem very general, a lot more general than sort of at least maybe people who work on pure maths think applied maths results can be. Are there any sort of applications where this doesn't work, where you'd like it to, sort of where the conditions sort of fail in real world settings? Or
Yeah, so like I think the simplest example that it doesn't work for is like shortest path, like Dijkstra, like because like in that sense, like it's sort of circular. So like the errors in that problem would propagate, like would blow up when like we sum it overall rounds, because like you just keep on picking like the wrong path. That's like a shortest path problem. So yeah, it doesn't work in that way.
yeah. And I guess I might misunderstand this, but my understanding is that these transformations are, it's not like we're showing they exist. We actually do have like a recipe to come up with the transformations.
Yeah.
Yeah.
Oh yeah.
Yeah. Then yeah.
This is showing its existence by like showing the transformation.
Yeah, by construction. Yeah. So I mean, how far away do you think this kind of stuff is from actual real world applications? And what sort of work needs to be done in between? As it be actually implementable, because it is real world applications.
So actually in terms of real world, like real world applications, a lot of applications, even though there are fancier algorithms, they do use greedy algorithms as benchmark, because like they are just like greedy is very simple to implement, so they might not be the most optimal ones, but it's pretty easy to directly apply this to like those greedy algorithms, I think, because like essentially in terms of implementing it, it's just a bunch of LP, but not like very complicated LPs, but yeah.
I did sort of want to ask a slightly more like, maybe general question, which is because we're at the Student Symposium Combinatorics, and most of the audience are working in would identify combinatorics, and because we've spoken like last year, we chat very briefly about particular problem. I was wondering if there were any problems in combinatorics that you'd like someone else in the audience to go and solve, so that your problems can be much easier to solve.
Yeah, actually there are. I think during my PhD, I did found like a lot of problems that I feel like it's the combinatorics problems, and like I don't know how to solve them, and like I think that's why I reached out to like more of my mathy friends, my friends that are actually doing combinatorics. You were one of them. Yeah. So yeah, because like sometimes I got confused, because like this looks very mathy, but I also don't know like where to start, or like if there's like a literature on it, and like yada yada yada. So the answer is yes, but on top of my mind, I don't think I can mention one. Yeah.
Well, I'm always happy to help, Suzanne. These kind of things are pretty cool, and I also really care about applications. Any more questions from the audience? I might give a little bit of more chance for people to put things in. Yeah, but I reckon this is maths is, I have no doubt in my mind that what you're doing in maths, you've got theorems and proofs. Some people who do pure maths don't have theorems. I mean, don't do theorem proof kind of thing as well. I consider myself one of in that category. All right, I think that's everything. Those are all the questions we have from the audience. Please join me in thanking Susan again for that wonderful talk. That was brilliant.